So in other words, it's not one of our basic 1 over x's. It's not one of our basic 1 over x squareds that are going to shift or graph easy. All right, so this you're going to have to put like a little bit more effort into. Okay, so on any of these, I can always find my domain, right? And I probably should find my domain. There's a connection between the domain and vertical asymptotes, or the domain and something called removable discontinuities. All right, so what I would do to start, I would, okay, well, can I come up with the domain? All right, well, I should be able to, right? Because it's a rational function. We've got this memorized at this point. We take that denominator and we set it equal to 0 because it can't be equal to 0. We're looking for those exclusions. So I'm going to take 2x squared minus x minus 1. I'm going to set that equal to 0, see if I can't come up with a domain. All right, so we're going to have to factor the left-hand side. So this one's a little bit more challenging. A lot of times what you've been given is just that's already been factored, or it's just been a nice little x minus 1. This is a trinomial. So I'm going to slide and divide because we all slide and divide, right? So I'm going to slide that 2 down. So x squared minus x minus 2. Now I've got that leading coefficient of 1. So then I can now guess and check and factor this kind of easy. I know this first term has to be an x, second one has to be an x. Only thing that multiplies together to be 2 is what? 2 times 1, right? So 2 and 1. Let's see, I need a negative 1 in the middle. So 2's got to be negative. Okay, now I slid, if we're doing slide and divide, I slid that 2. So now I've got to divide by 2. Okay, slide and divide. So this one's going to be a 2x plus 1. This is going to be an x minus 1. For people that can factor that just by guess and check, then you can go ahead and do it. You don't have to do slide and divide. All right, once you get to there, then I set both of them equal to 0. So from here, I get x equals a negative 1/2. Here I get x equals 1. Okay, so those are exclusions, right, from my domain. Those are exclusions. So that means those are the only 2 numbers not in the domain. Okay. And then I don't know how well you guys are getting this. All right, like, do you need to see a visual of that? All right. If you need to see a visual of that, you can put it on a number line and you can say, okay, well, here's negative 1/2. Here's 1. Negative 1/2 is not in the domain, so I put an open circle there. 1 is not in the domain, so I put an open circle there. And then all of these numbers are in the domain. All of these numbers are in the domain. All of these numbers are in the domain, right? Because these are my only exclusions. These are the only 2 numbers that would make that bottom 0. So this section, negative infinity to negative 1/2, negative 1/2. Helps if I write the right thing down. Negative 1/2 to 1. Skip over the 1, 1 to infinity. Okay, so for finding the domain, I can really easily set that denominator equal to 0. This took a little bit more work than the others. All right, but now what does that tell me? It tells me that these 2 numbers are not in my domain. So something has to be happening at those 2 locations for them not to be in the domain. Chances are, all right, on our domain, anytime we find values that have to be excluded, that's going to lead a direct result to my vertical asymptotes. Okay, because we do the exact same thing to find vertical asymptotes, right? We take the denominator, we set it equal to 0, that finds our vertical asymptotes. All right, but something that hasn't yet been brought up on this one is it also is going to talk to us about our removable discontinuities. They're called removable discontinuities. Now that's the fancy word for it, removable discontinuities. Or, nice plain little word, a hole. All right, it's going to create a hole. All right, because that's the only 2 things, for the most part, those are the only 2 things of why something is not going to be in the domain. It's either going to be a vertical asymptote or it's going to be a removable discontinuity, of which there's a connection between the domain and your vertical asymptotes. There's a connection between the domain and the removable discontinuities. All right, now, if this is the domain, I would have done the exact same thing to find the vertical asymptotes, right? Except what's the other step? After I come down here and I get to these 2, then I have to do what? I have to take these and plug them back into that numerator, right? So if I plug in a -1/2, that makes this -1 plus 1, that's 0. So the -1/2 is not a vertical asymptote, okay? Let me switch to a different color. Do I have another different color? I'm almost out of colors. Okay, so if I'm doing those vertical asymptotes, all right, I'm not going to rewrite all that. I got down to x equals -1/2. I got down to x equals 1. I plug them back in. When I plug that back in, that one doesn't work. So that's not a vertical asymptote. If I plug 1 in, I'm good, because that'd be 2 plus 1. That gives me 3. So the only vertical asymptote I have is 1. I didn't have to go through this again because I'd already done the math. All right, but then that means what? Then this -1/2 has to be something else. These two numbers are clearly not in the domain. So if it's not a vertical asymptote, that means that -1/2 has to be a whole or a removable discontinuity. Okay. Now let's take and do what you used to do in Algebra 2. You did this tons. You didn't even know why you were doing it. All right. But didn't you in Algebra 2, let's kind of block this off. Weren't you made to simplify these things? You took 2x plus 1. I'm just recopying the problem down. 2x squared minus x minus 1. Weren't you told to simplify it? You factored the top, you factored the bottom, and you crossed out things that you could, right? Okay, so I can't factor the top. 2x plus 1. All right, I already factored the bottom, so I factored this over here, so I don't want to factor it again. So this bottom factors into a 2x plus 1, and then an x minus 1, right? And then what did you do? In Algebra 2, you crossed out and you said, oh, that and that crosses out, leaves me with a 1 up there. So then you said that this was equal to 1 over an x minus 1. Okay, the thing is, they were trying to build you up to this point. If you cross something out, if I do something algebraic, okay, I did that. That's an algebraic technique. I crossed it out. If I cross it out, I'm removing a part of the graph and I'm creating a hole. Because aren't I removing it out of the algebra? If I remove it out of the algebra, then it's a removable discontinuity. It creates a hole in the graph. Okay. All right. So kind of let's take a look at this graph then. Okay. Trying to find a good place to graph it. All right, so from all of this over here, we figured out that there is a vertical asymptote at 1. So there's 1. So I can go ahead and put that on, because I know that exists. All right, now something that I didn't find, okay, but I couldn't I find horizontal asymptotes? Because we've got those memorized. Okay, so coming back and looking at that beginning, I've got an exponent of 1 in the top. I got the exponent of x squared in the bottom. So the bottom is bigger. When the bottom is bigger, what's my horizontal asymptote? 0. So that means I know I have one at 0, which those are going to be really, really hard to see. I usually just kind of do it along there. Okay, I could label them. Y equals 0 for that one. X equals 1 for that one. Now, I'm not going to do anything with this hole just quite yet, because I don't know exactly what this is going to look like. I mean, I could, if you guys were really good, you could maybe draw some conclusions over the fact, because we've done 1 over x and we've done 1 over x squared, right? And so this and this is probably going to look like a 1 over x one, right? Which would mean they're in opposite locations, which are here and here. All right, but if you can't draw that conclusion, all right, I can still figure it out pretty easily by doing what's called, well, I usually call it a calculus number line. It can be any type of number line I want. Okay, so let's say I want to use a number line. Now, if I'm going to do this and I'm going to look at these values, I'm going to take these two exclusions. And these two numbers are the two numbers I'm going to put on my number line. Okay, so I'm going to take this number line and I'm going to put my negative 1/2 on there. I'm going to put my 1 on there because that kind of divided up the entire problem. Okay, now if I assume that this is negative, or this is my function f of x down here, and then up here, these are 3 sections of the number line from all the way over here to negative 1/2, in between negative 1/2 and 1, and then over here from 1 to infinity, there's 3 sections. So this would be the interval from negative infinity to negative 1/2. This is from negative 1/2 to 1. This is from 1 to infinity. All right, now if I wanted to, I could do it by hand. I could just plug things in, see what happens here. All right, or I could use my graphing calculator if I really didn't want to have to do the math in my head. But if I take a really big negative number, any number in this interval, which negative 100, I could take something really ridiculously big. If I plug a negative number in the top, times 2, add 1, the top's going to be negative, right? I don't care what the number is, top's going to be negative. If I come down here and I take a really big negative number and I square it, it becomes positive, right? Times 2 minus a negative number, which means I'm really adding. So then there's positive number plus another positive number, and they're really big, minus 1. So this bottom's positive. So I ought to be able to in my head go, oh, well, this is negative divided by positive. That means every number in this interval is going to be negative, which means it's going to be below the x-axis. So that kind of verifies that in between negative 1/2 and here, my swoopy has got to be down here. All right, if I plug in 0, if I plug 0 into that top, I get a positive number. If I plug 0 in here, I get a negative number. Positive divided by negative means it's going to be negative here. So even in between negative 1/2 and 1, it still remains negative. And then if I pick a really big positive number, it doesn't matter what number I pick over here, but if I pick a really big positive number and add to it, that top stays positive. A really big positive number squared makes it really big, minus the big number minus 1, I'm still going to have a positive number. That's going to be positive divided by positive. Any number here is going to be positive. So if you want to test where something's going to be, you can test numbers. It's almost like using the XY table that you originally used when you first learned how to plot numbers. Okay, now this action of crossing this out, this negative 1/2, turns out to be a negative or a removable discontinuity. All right, negative 1/2 is, let's just say, roughly right about there. Okay, because negative 1 would be there. So it's roughly right there. Now, I know I have to hug this asymptote. I have to hug this asymptote, and we've already concluded that it's got to be negative in this whole entire section. It has to be negative in that whole entire section. So I'm going to hug here, but when I come down to negative 1/2, there's where my hole is. And then it's still negative, and it's going to hug here. Over here, anything to the right of 1, everything in that has to be positive. So it's going to be hugging here and then hug there. And didn't our basic 1/x graph have swoopies in 2 locations? Okay, now the only difference is this was way more complicated than just a plain 1/x graph or a 1/x squared graph. It was way more complicated. And what that did, it then created a hole, all right, that you can't see. And in our 1/x and 1/x squares, and we've been shifting those little baby functions, there were no holes. Okay, there were no holes. Okay, now if I stop sharing, let's go back to the graphing calculator again. All right, so obviously this is a different function. Let's clear that out. Let's put in the new one. What was this? 2x minus 1. 2x minus 1. 2x squared minus x minus 1. Okay, let's zoom standard on this. Okay, now the only thing that I missed, did I type that in right or did I do this wrong? 2x, oh, made a mistake. That's why the picture don't work. Let's make that a plus. And then there we go. Now let's try it again. Zoom standard. Okay, now there's the graph. Now, what's on my hand drawing that's not in this calculator window? The hole. The graphing calculator is not going to show you where the holes are. So that's why you're going to have to know what they are, where they come from, because the graphing calculator is not going to show you that. Okay, so if they talk about removable discontinuities or it talks about holes or anything like that, you find them by taking it, factoring, seeing if something crosses out, or from your domain, when you plug it back in, if in the domain we plugged it back in the numerator and it got thrown out. So if it gets thrown out, then obviously it's not a vertical asymptote. It has to be the hole. Okay. All right, so far so good.